Now Director of IM Group of Researchers, Professor Dr. Nasimullah Qureshi is with us to deliver his lecture on NMR spectroscopy. He is currently working as Chairman Department of Chemistry, University of Sawabi. He has completed his PhD from University of Innsbruck, Austria and postdoc from Chinese Academy of Sciences. His research contributions are internationally acknowledged, highly applicable, and have long-lasting impacts in industrial sector. Based on his research work, he has been awarded with OEED Research Fellowship, Austria 2022, Ernst March Award, Austria 2018 and 19, Chinese Academy of Sciences Fellowship for Postdoctoral Research Scholars from Developing Countries Award, China in 2014, and Research Productivity Award by Pakistan Council of Science and Technology. Sir, it's really an honor for us to have you on board. I request you to may start your lecture.
Ms. Kashif, can you hear me?
Yes, sir.
Okay, so can I start now?
Yes, please, sir.
Okay, so Bismillah ar-Rahman ar-Rahim, Assalamu alaikum to all of you and good morning. I'm Professor Dr. Muhammad Nasimullah Qureshi, is introduced by Ms. Kashif. I will talk, today I will talk about the nuclear magnetic resonance spectroscopy, and I will try to sum up all the things because it's a very big topic and we can talk a lot of, we can have a separate coursework as well. So a lot of has been written on this topic, and so I will try. Just a minute. So, can you see my slides? Hello?
Yes, sir.
Your first slide is visible.
Yes, sir.
Yes, sir.
So my slides
Yes,
are
sir. We
moving,
can see it. Please.
moving as well. Hello?
Yes, sir, they are movable.
Okay. So this is the nuclear magnetic resonance spectroscopy. Nuclear, is the name indicates, the nuclear. It's about the study of the nuclear spins, the magnetic under the influence of the applied magnetic field, and resonance is the resonance of the nuclei. Or specifically, we will talk about the proton resonance and the carbon-13 resonance. So, nuclear magnetic resonance is about the nuclear spin under the influence of the applied magnetic field, and the resonance part is to record the resulting resonance in nuclear spin through the absorption of radio waves. So, at a glance, or in one view, we can say that the NMR radio frequency is absorbed, and as a result of this absorption, the nuclei placed under the static magnetic field changes their spin after the absorption of the radio frequency radiations, and the information we deduced are the electronic and environment of the nuclei, their number and number of the neighboring atoms. So all about the structure of the molecule, and within the molecule, as the NMR is mostly we can say mostly applied in the organic to determine the structure of the organic molecule. So normally we talk about only the proton and the carbon NMR, and also there are specific like the hydrogen H1 proton NMR spectroscopy and carbon-13 nuclear magnetic resonance. So this is the comparison. This slide shows the comparison with other spectrometric and spectroscopic techniques, because NMR itself, I will confidently say that no method is absolute. So all the methods have, some information are more information from one method and some other information from other methods. So NMR in combination with other
Excuse me, sir.
spectrometric.
Your screen is not visible.
Okay, but
kindly share it again, and I request all the participants do not share their screens, otherwise the presenter's screen will not be visible. Don't turn on your mics and don't share your screens.
I will just stop sharing and then we'll start again. Is it okay now?
Yes, sir, it's fine.
So can I go on now? Yes?
Yes, please.
Okay. Okay, so this is about the comparison. The slides in front of you is the comparison with other spectrometric and spectroscopic techniques. As I told you earlier, that NMR itself cannot determine absolutely the structure of the molecule, but with other methods like the MS, like the IR, like the UV. So all these data will give you the structural information of the molecule and that molecule under the study. So this is, I mean, some of the information are deduced from the NMR experiments, and some of the information are deduced from the mass spectrometric methods, and some of the information from the IR or the UV spectroscopic methods. And also there are some limitation, like for example, we can like for example the sample, the amount of the sample or the scale we use in the NMR, in the proton NMR, C13 NMR, and in the MS and in the IR. Specifically, for example, I can say that the structure, the functional group can be determined using the NMR and the IR, but the mass spectrometric method will not give you the functional group information. Similarly, the carbon connections can only be determined, or can only these information can only be deduced using the NMR, and also the stereochemistry and the radio stereochemistry. These information can be deduced from the NMR, but not from the MS and from the IR or from the UV spectroscopic method. So this is somehow about the comparison with other spectrometric and spectroscopic methods. Or we can say the limitations of different spectroscopic and spectrometric methods. So just a bit of introduction of the nuclear magnetic resonance spectroscopy. So nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize organic molecules by identifying carbon-hydrogen framework within the molecule. So mainly it determines the carbon and hydrogen framework, and because we are the specifically, for example, I am the organic chemist, so we organic chemists are interested in determining the carbon hydrogen framework of the molecule. So two common types of the NMR spectroscopy are used to characterize organic structure. That is the H1 or the proton NMR is used to determine the type and number of the hydrogen atoms in a molecule, and C13 NMR is used to determine the type of carbon atoms in the molecule. The source, so because we are using the H1 and C13, so we will explain in the later slides. So that's why I'm not explaining these things at time, just to make it fundamental, or to make it basic for the other slides, for the next coming slides. The source of energy in NMR, as earlier explained, is the radio waves, which have long wavelengths, so less energy waves, and wavelengths is very long. So thus low energy and frequency. When low energy radio waves interact with the molecule, they can change the nucleus spin of some elements, including H1 and C13. So we are only limited to the nucleus spin, not the electronic excitation, not the vibrational and other excitation, but only spin flip. So we will discuss only the spin flip or the spin excitation. So within the spin, because there are different quantum numbers, So principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So we will limit our presentation to the spin quantum number. Introduction to this is also a continuation of the introduction to the NMR spectroscopy. When a charged particle, so proton is a charged particle, similarly the electron is also a charged particle, so we are more focused on the proton. So when a charged particle such as proton spins on its axis, it creates a magnetic field. So proton spins on its axis, so it creates a magnetic field. Thus, the nucleus can be considered to be a tiny bar magnet. Normally, these tiny bar magnets are randomly oriented in space. So without applying the magnetic field, they are randomly oriented. So you can see at the bottom of the slide that on the left side there is a spinning proton. You can see the spinning proton, and within the middle, without the external magnetic field, they are randomly oriented. However, and on the right side, there is when you are applying the magnetic field. So, however, in the presence of a magnetic field, they are oriented with or against this applied field. So more nuclei are oriented with the applied magnetic field because this arrangement is lower in energy. So when the field is applied, with the magnetic field is applied, so some of the proton are oriented along with the magnetic field and some are against. So the energy difference between these two states is very small, but there is an energy difference between the alignment with the magnetic field and alignment against the magnetic field. So automatically alignment against the magnetic field is a high energy state and alignment with the magnetic field is low energy state. So this is again the same thing, that without the magnetic field, the proton are randomly oriented, and when the magnetic field is applied, so there are some are proton, some proton are oriented against the magnetic field, and some are aligned with the magnetic field. So, and also at the bottom, this is just to show that the spinning proton is like a magnet. And this is the spinning, how the spins around the proton spins around the axis. In a magnetic field, there are now two energy states. Now, when the field is applied, so two energy states are created, and these two energy states for a proton, a lower energy states with the nucleus aligned. So nucleus, when we say the nucleus, so we mean the proton. Low energy states with the nucleus aligned in the same direction is magnetic field. So B naught is the magnetic field, and a high energy states in which the nucleus aligned against the magnetic field. When an external source energy that matches the energy difference between these two states is applied, energy is absorbed, causing the nucleus to spin flip. So the spin flip occurs when the external source of energy is applied, and the frequency of the external source of energy should match the energy difference between these two states. Then the spin flip will occur from one orientation to another orientation. So the energy difference between these two nucleus spin states corresponds to the low frequency radio frequency or radio waves region of the electromagnetic spectrum. And this is again the same thing, that at the beginning there is degenerate spin state. I mean to say that all the proton have the same spin states, but when the magnetic field is applied, so some are against the magnetic field and some are aligned with the magnetic field, and the energy difference is equal to h mu. Thus, two variables characterize NMR. So there are two variables. One is the applied magnetic field, the strength of which is measured in Tesla, and the frequency mu from the external external radiation or the external energy stores used for resonance, and that is measured in hertz or megahertz. So in most of the cases, you might have heard, and you might have, also we will discuss in this that we only determine the strength of the NMR using the megahertz or hertz, not the Tesla. But you can say that so much Tesla NMR. So the frequency needed for resonance and the applied magnetic field strength are proportionally related. NMR spectrometers are referred to as I told you, so 300 megahertz instrument, 500 megahertz instrument, and so forth. So at the very first slide, I have shown 900 megahertz instrument, the NMR, depending on the frequency of the radio waves used for the resonance. These spectrometers use very powerful magnets to create a small but measurable energy difference between two possible spin states. And this is just the diagram or the structure of the NMR. So we are having the superconducting magnet, the NMR console, and this is the recording device. And within this, so sorry. Just bringing it to this slide mode. So you can put your sample over here at the red arrow, and it will goes down, and then the NMR experiment will start. And this is inside the superconducting magnet. So the sample is placed over here, and this is the chilling procedures, and this is the magnetic field is applied over here. So I will not talk in detail about the instrumentation of the NMR, because it will take a lot of time of us, but just to present this slide. So the NMR machine is basically a big and expensive FM radio. So it has a magnet, superconducting, some electromagnets, and permanent magnets still around. So these are the magnets. So you can see the north and south pole. The frequency generator creates the alternating current that induces continuous wave or pulsed. Detector subtract the base frequency, a constant frequency very close to mu naught, to the output frequency. It is lower frequency and much easier to deal with. And we need a recorder, the XY plotter, or the computer, etc. But nowadays we are using the computer. Why to bother learning? So this is, I mean to say, why we should do the NMR study. So the structure, more we are interested to perform the NMR experiments and to perform the NMR study for the structure elucidation. So structure elucidation, the chemical structure of the molecule, and mostly the natural product chemist and the synthetic organic chemist for the analytical tool of choice for the synthetic chemist. Study of the dynamic process, the reaction kinetics, and the study of equilibrium of the reactions. Structural three-dimensional studies of the protein, the DNA complexes, polysaccharides, and also we bother to learn the NMR for the drug designing, that is the SAR, and also in the medicine for the magnetic resonance imaging, the MRI. This is also the NMR. So mostly the NMR is applied by the natural product chemist. Natural product chemists are still the largest group who are using the NMR spectroscopy for the structure elucidation. NMR and the natural product chemists are generally small in quantities. The natural products are generally small in quantities, novel in structures, possess chirality, have changing conformations and capacity to interact with large biomolecules. It's again the same thing. So we are studying the NMR, or the application of the NMR for the structure elucidation, for the studying of the dynamic processes, for the three-dimensional structure, the drug designing, that is the MRI, or for the SAR relationship, and also in the medicine, the MRI. Now, what NMR can measure, or what information we are getting from the NMR spectroscopy? So the most important thing is the functional group analysis, and this can be done by getting the chemical shifts. So we will discuss what is chemical shift, and also the bonding connectivity and orientation. So bonding connectivity, or we can say the scalar coupling, and the orientation, and also the dipolar coupling, or the Overhauser effect, the J coupling. Through space connectivity, Overhauser effects, molecular conformation, DNA, peptide, and enzyme sequence and structure, and the chemical dynamics. So these can be measured using the NMR. And this is the typical protocol, because you can vary, but this is a very typical protocol that normally you do the one dimension, because in NMR there are two types of spectrum, I will say. You are getting two types of spectra: one-dimensional spectra, two-dimensional spectra. And in one dimension, normally we say the proton NMR and carbon 13 NMR. So the typically first you perform the proton NMR, that is the and you are getting the proton NMR spectrum, the H1 spectrum information, and give you the information about the chemical shifts, coupling constants, and integrals. And then you are performing the COSY, the two-dimensional NMR, the proton-proton correlation. So you are determining the proton-proton correlation, and this is homonuclear. As the proton-proton, so homonuclear. So it identifies the J coupling relationship between the protons. And then carbon 13 NMR experiment is performed, and it gives you the information about the carbon counts and multiplicity. And then the heteronuclear experiments like the HMQC, HSQC, HMBC, and the nuclear Hauser effect, NOSI, and TOXI, two-dimensional NMR spectroscopy is performed. So this is a typical protocol, but you can vary as per your need. This is as we told in the previous slide, there are one-dimensional NMR spectroscopy and two-dimensional or multi-dimensional NMR spectroscopy. But in most of the cases, we are using the one-dimensional and two-dimensional NMR spectroscopy. And in one-dimensional NMR spectroscopy, there is H1 NMR and C13 NMR spectroscopy. And in two-dimensional NMR spectroscopy, there is a homonuclear and heteronuclear NMR spectroscopy. So in two-dimensional, basically, the information you are getting are plotted on the two axes. That is the x-axis and the y-axis. And then they are compared, or they are correlated with one another, and you are getting the homonuclear correlation and heteronuclear correlation. So in the homonuclear correlation, mostly the COSY, 6C, or the TOXI, or the NOSI, ROSI, DOSI. So there are a number of correlations are there, number of correlation spectroscopy are there. And in the heteronuclear correlation, this is the carbon and hydrogen. Like for example, in the homonuclear, you are plotting same the spectrum obtained from the same nuclear spin. Like for example, H1 NMR spectrum is plotted on the one x-axis and in the on the y-axis. And in the heteronuclear spectroscopy or spectrum, the different nuclei spectrum are plotted. Like for example, the H1 NMR spectrum is plotted on x-axis, and C13 NMR spectrum is plotted on the y-axis. And within this heteronuclear, NMR spectroscopy, there is HMQC, HMBC, and HSQC like that. So the different abbreviation we are using, that is the different two-dimensional NMR techniques, double irradiation or spin-spin decoupling, depth. So depth is the abbreviation of distortion enhancement of NMR signals by polarization transfer. Inept, insensitive nuclei enhanced by polarization transfer. So depth and inept, mostly it gives the more same information, more or less same information. And similarly, the nuclear Overhauser effects. So different spectra are there. J-resolved two-dimensional coupling, two-dimensional NMR spectroscopy, and COSY. COSY is homonuclear correlated. So homonuclear correlation is obtained from the COSY. Correlated spectroscopy. Hit core, heteronuclear shift correlation. NOSY, nuclear Overhauser effect spectroscopy. Inadequate, so it is the abbreviation basically incredible natural abundance double quantum transfer experiment. HMBC, heteronuclear multiple bond correlation. So it is multiple bond correlation, not single bond correlation, multiple bond. So the protons, proton and carbon, which are correlated through the multiple bond, not through the single bond, are connected through the multiple bonds. And HSQC, heteronuclear single quantum coherence. HMQC, heteronuclear multiple quantum coherence. So this is the explanation in another way. That is, as I told you, the scalar coupling and dipolar coupling. So within the scalar coupling, there is the homonuclear scalar coupling, COSY, TOXY, multiple quantum, and in the heteronuclear scalar coupling, HSQC, heterotoxy, HMQC. And in the dipolar coupling, that is the environmental, like I mean to say, the in space coupling. So NOSY, HSQC, NOSY, HMQC. So you will these are the abbreviation for different coupling, like the scalar coupling and the dipolar types of the scalar coupling and types of the dipolar coupling. So again, to continue the introduction, so now we will introduce we will be more focused on the H1 NMR spectroscopy. So protons in different environment absorb at slightly different frequencies, so they are distinguishable by NMR. The frequency at which a particular NMR absorbs is determined by its electronic environment, because the proton has different electronic environment. Proton is within the nucleus, and the nucleus is bounded by the shells, and in the shell there are electrons. So because if the external source is irradiating or giving the energy to the proton to the nucleus, so first they have to interact with the electronic cloud in the shell, or first they have to interact with the electron, or first they have to fight with the electron so as to reach the proton within the nucleus. The size of the magnetic field generated by the electrons around the proton determines where it absorbs. So as I told you, first the external field will interact with the electron in the shell, and then it will reach the proton in the nucleus. Modern NMR spectrometers use a constant magnetic field strength, and then a narrow range of frequencies is applied to achieve the resonance of all protons. So only, and which nuclei will be NMR active? So there's, as I told you before, that we will explain later, only nuclei that contain odd mass number, like the H1, C13, F19, phosphorus 31, are odd atomic numbers, such as 1H2. So in the 1H2, the mass number is even, but the atomic number is 1. And N14, again, N14 has even mass number but odd atomic number, give rise to NMR signals. So these nuclei are NMR active, and you can perform, like for example, as we are focused on the H1 NMR, C13 NMR, but you can have F19 NMR, P31 NMR, and so on, having the odd mass number, odd atomic numbers. And how the spectrum, when you are performing the NMR experiment, it looks like. So in the classic, we are having upfield and downfield. So on the right side it is upfield, and on the left side it is downfield. Just keep these things in mind, and then you will understand how it will be like in the later spectra. So it is the NMR. It will be on the right side. It will be the upfield, like the high field strength, and the signals on the on the left side will be on the downfield strength side. So this is the typical spectrum that, for example, we are having the TMS as the reference standard, or the internal standard, and then the rest of the molecules occurs on the left side, that is on the downfield. So it means that the TMS, the tetramethylsilane is used as a reference, because in this case, in this molecule, the proton are highly shielded. The proton are highly shielded than rest of the molecules. So the TMS will need much more energy, or the much more energy, or the external source of energy will be given in much more strength, so as to occur the spin flip in the TMS. But here we placed it at the 0 ppm, because it is arbitrarily taken as 0. It is not 0, but it is arbitrarily taken as 0. So it is at the highest field strength, and the radio frequency is the strongest. Radio waves are used to bring about the spin flip in the TMS. So this is arbitrarily taken as 0, and the rest of the molecule is on the downfield side. So it means that low energy is used for rest of the molecule other than the TMS. So it will the signals for rest of the molecule will occur at the downfield side. So the NMR absorptions generally appear as sharp peaks. Increasing chemical shift is plotted from left to right. Most proton absorbs between 0 to 10 ppm. And the chemical shift, the information regarding the chemical shift is measured in ppm, parts per million. The term upfield and downfield describe the relative location of the peaks. The relative location, the word relative is in relation to TMS, that's the internal standard. Upfield mean to the right, downfield mean to the left of the internal standard. NMR absorptions are measured relative to the position of a reference peak at 0 ppm on the scale due to the tetramethylsilane. TMS is a volatile inert compound that gives a single peak upfield from typical NMR absorptions. So this is the structure of the tetramethylsilane. As the silicon is in the carbon family, so it is not so much electronegative. So and the CH3, these are the, I mean to say, this is the sp3 hybridization is there, and as a result of this sp3 hybridization, the hydrogen, the proton in this TMS, all they are highly shielded. Highly shielding means that the electronic structures, or the electronic cloud, shields the proton from absorption of the external energy source. So first they interact with the electronic cloud of the tetramethylsilane, and then they reach So much more energy is needed to interact with the electronic cloud, and then so that's why the TMS is absorbing much more energy, and it is placed at the upfield and arbitrarily taken as zero. So tetramethylsilane having the 12, and all the protons are equivalent. They are having the same environment. So with 12 equivalent protons to give a strong signal. It is volatile. Its boiling point is 29 degrees Celsius, so can easily be removed from the sample. It usually does not react with most compounds, so it is inert to the compounds as well. That is why it is used as an standard standard. Its resonance is arbitrarily taken as zero, and in other molecules the resonance will appear below this. Therefore, the value are given positive sign downfield from TMS, which is given zero value or 0 ppm. So the chemical shift of the TMS is arbitrarily taken as zero on the scale. Now the spectrum are and what information we are getting from the spectrum. The chemical shift of the x-axis gives the position of an NMR signal measured in ppm according to the following equation. So it is this is the equation for determining the chemical shift in ppm. So observed chemical shift in hertz downfield from the TMS, and mu or the frequency of the NMR spectrometer. So by reporting the NMR absorption as a fraction of the NMR operating frequency, we get units ppm that are independent of the spectrometer. So four different features of a proton NMR spectrum provide information about a compound structure. So these information we are getting from the proton NMR spectrum. Number of the signals we are getting. So how many numbers? So you can see the number of the signals in the spectrum. Position of the signals. So position of the signals corresponds to the chemical shift values on the spectrum. Intensity of the signal, so you can see how much intense is the signal, and spin splitting of the signal. Also you will get the information of the splitting, because when you zoom the signals, so you will see the splitting, how the each signal of each proton is splitted, and this splitting is because of the environment of the proton. So now each information, number of the signal, position of the signal, intensity of the signal, and spin splitting of the signals. So we will discuss each one by one. Number of the signal, the number of NMR signals equals the number of different types of proton in a compound. So simply different types of proton. So all the equivalent proton will give you one signal. So different or non-equivalent protons will give you the number of the signals. I mean to say, so number of the signal NMR signals correspond to different types or different non-equivalent protons. Proton in different environments give different NMR signals. So means non-equivalent proton, different non-equivalent proton will give different signals. Equivalent proton give the same NMR signal. So you can see in the slide that these protons, for example, these proton on the left side, these are the same. So HA and HA designated as in this ether compound, they are having the same environment on either side, so they are equivalent. So it will both, for example, all these 6 protons will give you one signal. It will be intense, but one signal. It will give you one signal. And this is the chloroethyl chloride. So and the 5 protons are not equivalent. So 2 protons, they are equivalent, and similarly these 3 protons are equivalent. So but the methyl group and this CH2 group and this CH3 group, they are having non-equivalent proton. So 2 types of hydrogens are there. So 2 NMR signals will be observed. And in this case, on the right side, in the molecule, on the right side, ethyl, methyl, ether. So there are 3 types of hydrogen you can see. So HA designated as HA, HB, and HC, and you will get the 3 NMR signals. So to determine equivalent proton in cycloalkane and alkene, always draw all bonds to the hydrogen, because you have to draw the bonding. Then you will understand that whether the hydrogen are equivalents or non-equivalent. So you can see the environment, and from the environment you can decide whether the hydrogen are equivalent or not. So again, the number of the signals, as I told you before, that different proton or non-equivalent proton will give you different signals. Equivalent proton will give you same signal, one signal. So in comparing two hydrogen atoms on a ring or double bond, two protons are equivalent only if they are cis or trans to the same group. So, for example, in this, in the left side, the proton are cis to chlorine. So there is one type of hydrogen, so one signal you will get. And in this case, the environment is different on either side of the double bond. So the hydrogens are cis to, this is cis to chlorine, and this is cis to bromine. So they are having in the environment there is bromide is there, and in the HA environment there is chloride is there. So they are non-equivalent to each other. So you will get two non-equivalent protons are there, so you will get two signals. And in this case, there are three protons are there, three non-equivalent protons are there, so you will get three NMR signals. And so on. For example, the non-equivalent proton will give you the signals. So number of the signals correspond to the number of non-equivalent protons. And also you will determine because anisotropic and distereotopic protons can also be determined. And for example, in the left side, the hydrogen HA and HB are anisotropic proton, and when substitution and how they can be determined to be anisotropic enantiomers of one another. So when substitution of two hydrogen atoms by Z forms enantiomers, for example, on the right side, you can see these are the enantiomers. Enantiomers are the mirror images of one another, but not superimposable. Right? The two hydrogen atoms are equivalent and give us same NMR signal. So one NMR signal in the case of enantiomer. So these two hydrogen atoms are called enantiotopic proton. And distereotopic proton, in this case, the proton, the HA and HB, the designated the proton are HA and HB. Like for example, when substitution of these two hydrogen atoms by Z forms distereoisomers or distereomers. Distereomers are not mirror images and not superimposable. Enantiomers are mirror images and non-superimposable. Distereomers are not mirror images and non-superimposable. Right? So the two hydrogen atoms are not equivalent and give the two NMR signals. So these two hydrogen atoms are called distereotopic. So just to sum up this part, that the non-equivalent proton will give you different NMR signals, equivalent proton will give you same NMR signal. And now coming to the position of the signals. So in the vicinity of the nucleus, position of the signals means signal arises at which position of the spectrum or at which value of the spectrum. So in the vicinity of the nucleus, the magnetic field generated by the circulating electron decreases the external magnetic field that the proton feels, as we explained earlier. Since the electron experiences a lower magnetic field strength, it needs a lower frequency to achieve resonance. Lower frequency is to the right in NMR spectrum towards a lower chemical shift. So shielding shifts the absorption upfield. When the proton is shielded, so much more energy is needed. When the proton is deshielded, so low energy is used. As in the case of the TMS, much more energy is needed, so it is on the upfield on the right side, and the rest of the molecule, the proton and the rest of the molecule are not so much shielded. They are shielded, but not so much shielded as comparing to the TMS. So they are giving the signals on the left side, that is the downfield. So they can be said that the rest of the proton, the proton and rest of the molecule other than the TMS are somehow de-shielded in comparison to that of the proton in the TMS. The less shielded the nucleus becomes, the more of the applied magnetic field it feels. So when shielding is less, so the applied magnetic field is more effective on the proton. This de-shielded nucleus experiences a higher magnetic field strength. It needs a higher frequency to achieve the resonance. Higher frequency is to the left in NMR spectrum towards higher chemical shift. So as higher chemical shift mean downfield, because the chemical shift that TMS is taken as arbitrarily taken, because I'm using the word arbitrarily, it is not zero, but arbitrarily we imposed zero value, we imposed a zero value of chemical shift to the TMS. So de-shielding shifts in absorption downfield. Protons near electronegative atoms are de-shielded because the electronegative atom, they catches the electron, or they pull the electronic cloud towards itself. So the electronic cloud, the effect of the electronic cloud on the proton is less. So that's why they are somehow de-shielded in case where the proton is connected to the electronegative atoms. So they absorb downfield, or they absorb they feel the electronic the magnetic field much more. So this is how again the for example, in the case of the this is in this side there's the shielding effect, and this again the de-shielding effect. For example, you can see CH4. In the case of the CH4 methyl group, this is sp3 hybridized. Also in this CH3Cl, the carbon is sp3 hybridized. But in this case, CH4, there is no electron. All the hydrogen are hydrogen. I mean to say, in this case, one hydrogen is replaced by chloride atom. So chlorine is electronegative element. So that's why it will the electronic cloud in the CH3 group is somehow pulled towards the chloride, so decreasing the effect of the electronic cloud in the CH3 group. So that's why the CH3, the proton in the CH3 group, are somehow de-shielded in comparison to that of the CH4. So the CH4, the proton in the CH4 will give somehow nearby to TMS, or somehow near towards the TMS, but the signals in the CH3, in the proton of the CH3Cl methyl chloride, they will give towards the left side of the TMS, or left side towards the of the CH4. So this is again the same thing, the shielding and de-shielding effect. And this is the position of the signal. So the HB in this case, for example, you can see the designated proton HA and HB. The HB protons are de-shielded because they are closer to the electronegative chlorine atom, so they absorb downfield from HA. So more towards the electronegative atom, so de-shielding is more. In the second case, because fluorine is more electronegative than bromine, so the HB is much more de-shielded than HA. And again, as the de-shielding, so they will absorb, de-shielding is more, so they will absorb downfield from the other proton, shielded proton. So this is again the effect of the shielding and de-shielding. And this is the chemical shift values of different. This is again the same thing of the that is the position of the signals, because the chemical shift corresponds to the position of the signals, or the position of the signals correspond to the chemical shift values. Now, what is chemical shift? Basically, chemical shift value or chemical shift is defined as, this is the resonance position of a proton relative to an internal standard, because it is relative to, this value is relative. It is not absolute value, it is relative value to an internal standard. And this internal standard, in most of the cases, the TMS is used as an internal standard in the NMR experiment. Protons in a given environment absorb in a predictable region in an NMR spectrum. So these are the different chemical shift values in which such groups occurs. For example, you can see the table. This is the sp3 hybridized CH4 like that. So the chemical shift values, the region, it gives the signals in 0.9 to 2 ppm in the spectrum, and so on like that. For example, in this case, this is the ethylene group, so it gives you the 2.5. In this case, this is the sp hybridization is there, and when the electronegative element is there, so the de-shielding is more, so the chemical shift value will be higher. For example, you can see in this aldehyde group and carboxylic acid group, the chemical shift values is 9 to 10 ppm in case of the aldehyde, and in case of the carboxylic acid group, because there is oxygen, the carbon is attached with the oxygen double bond, and in this case, on the other side, the carbon is attached with the hydroxyl group. So this is the 10 to 12 ppm, and so on. You are decreasing the de-shielding, you will get higher chemical shift value. So this is again the same thing. The chemical shift of carbon-hydrogen bond decreases with increasing alkyl substitution. So the chemical shift value will be increased with the increasing alkyl substitution with the carbon-hydrogen bond. So this is the same thing, the chemical shift value as we discussed before. In a magnetic field, the 6 pi electron in the benzene, because this is typically related to the benzene, circulates around the ring, creating a ring current. So there are pi electrons are there, and they are creating a magnetic field, like the ring current is there. The magnetic field induced by these moving electrons reinforces the applied magnetic field in the vicinity of the proton. The proton thus feel a stronger magnetic field, and a higher frequency is needed for resonance. Thus, they are de-shielded and absorb downfield. So the protons are de-shielded, the absorption is downfield at 6.5 to 8 ppm. So on much more higher side of the chemical shift. In a magnetic field, the loosely held pi electrons of the double bond creates a magnetic field that reinforces the applied field in the vicinity of the proton. The proton now feels a stronger magnetic field and requires a higher frequency for resonance. Thus, protons are de-shielded and the absorption downfield. I will take a little bit more time because it will take a lot of time for me. So I will take a little bit more time than as we discussed before. Is it okay?
Yes, sir, you may continue.
Okay. So this is again as we discussed before. I'm just skipping these things. So these are the table. You can see this table in a number of books, and you can also Google these things as well. So that's just to show you the shielding effect and the de-shielding effect. That when the de-shielding is there, so the chemical shift value will be higher. When shielding is there, the chemical shift will be lower. So it will be nearby. So much the shielding is there, so it will be near to the TMS. When the de-shielding is there, it will be away from the TMS value, which is 0. Again, it shows different groups or different molecules giving signals at different chemical shifts. This is again the same thing, the same table in different ways. So now the intensity of the signals. So the area under an NMR signal is proportional to the number of the absorbing protons. So the intensity of the signals will give you, for example, as I told you, that's equivalent proton. If they are 6 proton, if they are more than 6 proton, if they are 2 protons, if they are more than 2 protons, if they are equivalent, it will give you same one signal. So how you will determine that how many protons are equivalent, and this can be determined from the intensity of the signal. So the intensity of the signal will give you how many number of equivalent protons are there. So this is just to sum up this slide. For example, you can see these are the bars are there, and from these bars you can determine the intensity of the signal, because these bars are given by, I mean, you can measure by the measuring tool, or the software will give you the measurement of these intensity as well. So this is how to determine the number of protons giving rise to the NMR signal. So this is just to determine the intensity of number of equivalent protons. Now the spin splitting, like the environment of the proton. So also this information we are getting from the proton spectrum, proton NMR spectrum as well. The spin splitting, because this splitting is because of the environment. So for example, you can see that in this case there are, for example, you can see the CH2 CH, and in one case on one side there are two bromine atoms are there, and on the other side there are one bromine. So there are two types of protons. So it will give you two equivalent two signals. And this splitting, for example, how will you determine that how much splitting from the structure of the molecule? You can determine that which signal will be splitted by how many number of signals, or what will be the multiplicity. So multiplicity is normally calculated by the formula n plus 1. N is the number of the neighboring proton attached with the neighboring carbon, plus 1. So for example, in the case of the CH2 is attached to CH. So there is one, the signal of the CH2, the proton in the CH2 group will be splitted. For example, this is, and also you can see the shielding and de-shielding effect as well. For example, in the case of when there is two bromine, the CH, the proton in the CH, or the proton in the CH group, which is attached with the two bromine atom, or nearby two bromine atom, it is much more de-shielded than the proton in the CH2 group, which is attached with the bromine atom. So this the less shielded proton will be towards the TMS, and the chemical shift value of this CH2 group will be less as in comparison of the signal of the chemical shift value of the CH. So this CH is nearby to CH2, is in the neighbor of the CH2, and in the case of the CH2 there are two protons. So the signal of the CH proton will be splitted by 3. So you can see this is splitted by 3, because for example there are two protons, so 2 plus 1. So this is the signal of this proton, CH proton, and it is splitted by 3. So its multiplicity is 3. So this 3 means that this 3 means when you see triplet signal, so it means that this proton has neighboring protons 2. And similarly, for example, this CH2 group, the signal of this CH2 group will be splitted by 2 signals. So it will give you a doublet signal. Doublet signal will be given, which means that this CH2 group is attached with the carbon having 1 proton. So this also determines the environment of the. So all these information will give you the structure of the molecule. So spin-spin splitting occurs when only between non-equivalent protons on the same carbon. The equivalent proton will not split. It will not give you the spin-spin splitting. So spin-spin splitting occurs between the non-equivalent proton on the same carbon or adjacent carbon. Now, so the rest of the things we already explained. And also this we explained that how you are getting the equivalent proton will give you a signal, non-splitted signal or singlet. Non-splitted signal, singlet. So one signal will be given, and when there are multiplicity, when the adjacent protons are there, so it will give you doublet signal, triplet signal, multiplet signal, and so on. This also we explained that how the adjacent things, because in this spectrum already on one side there are two bromine atoms are there, and on the other side there is one bromine atom. So there are two types of protons are there, and also in the case of carbon, which is the hydrogen which are attached to the carbon, which is then attached with the two bromine atoms. So here the electronegativity, the electronegative elements are much more, so the de-shielding will be much more. So the chemical shift value will be high in comparison to the carbon which is attached to the bromine, single bromine atom, and this carbon, the HA and HB, the chemical shift value of the signals given by the HA and HB, they will give you, because they will give you the chemical shift value will be towards the TMS, towards the high, because here the shielding is less in comparison to this CH group. So again, this is the how the multiplicity or the spin-spin splitting is there. So you are getting when there is no neighboring proton, so singlet is there. When there is neighboring proton are there, so it will be doublet, triplet, multiplet. Now you can determine from the structure using the formula n+1. I'm just skipping these things. And these are the different, for example, you can see the name of given number of peaks. So number of if there is one peak, one signal, so singlet, doublet, triplet, quartet, quintet, sextet, septet, and so on. So on, multiplet is used for the word. So this is the table of different multiplicity. Just skipping these things, just to see the splitting pattern. And this is again because this is different correlations, because for example sometimes you will see that a signal is splitted by one proton, and then it is splitted again by another proton. On one side, this is, for example, here it is, this single is splitted by into four, and then these four are then again splitted each one into two. So 4 multiplied by 2 into 8 octet. So you are getting much more. So multiplet, you will get a multiplet. So the spin splitting will give you the vicinity or the environment of the environmental structure or the environmental protons of the proton under study. So this is again regarding the splitting, splitting of the how hydroxyl proton is having these things. So this is the so these are the different protons, cyclohexane conformers, benzene structure like that, and also I'm just skipping these things. Now to compare these things, because we are going towards the C13 NMR. So just to compare these two, just to make a fundamental of the C13 NMR. So both gives us information about the number of the chemically non-equivalent nuclei, non-equivalent hydrogen or non-equivalent carbon. Both give us information about the environment of the nuclei, that is the hybridization state, attached atom, etc. It is convenient to use FT-NMR. Nowadays, we are using the FT-NMR in both the cases. Because FT-NMR Fourier transformation of the NMR signal. So Fourier transformation is a mathematical Fourier transformation is a mathematical formula. So you are getting digitalized data, Fourier transformed data. So C13 FT-NMR, because the signal for carbon, but in this case the signal for the carbon, because the most important thing is the intensity of the signals in the C13 NMR is much more weaker. So that is 10 raised to power minus 4 times weaker than the signals for a hydrogen atoms. A signal for a C13 nucleus is only about 1% as intense as that of a hydrogen or proton NMR because of the magnetic properties of the nuclei and the natural abundance level. Only 1.1 of all the carbon atoms in a sample are C13. So when you compare the abundance of the C13 and C12, so the abundance of the C13 is 1.1 of all the carbon atoms. C13 signals are spread over a much wider range than the proton signal, because in the case of the proton, we are having the chemical shift up to 10 ppm or 20 ppm. So, but in the case of the C13, it is more than the 200 ppm. So the chemical shift values is spread over a wider range than that of the proton NMR spectrum. So there are this is the figure for the this is the spectrum of the H1 NMR, how it looks like, and this is the spectrum of the C13. You can see the signal. So each different carbon will give you a signal. So to study the C13 NMR is a little bit easier than that of the proton NMR, because in that case the splitting is much more the H1 NMR spectrum is much more complex than that of the C13 NMR. And you can see the range, the range and the X value, and that is it ranges are it's spread over a wide range from 0 to 200 ppm. But in the case of the proton NMR, it is up to 10 ppm. So a separate distinct peak appears for each of the carbon, non-equivalent carbon. So this is the C13 spectra are easier to analyze. As I told, C13 spectrum or spectra are easier to analyze than proton spectra because the signals are not split. Each type of carbon atom appears as a single peak in the case of the C13 NMR spectrum. The lack of splitting in C13 NMR spectrum is a consequence of the low natural abundance of C13. So this is the reason of the no splitting. Recall that splitting occurs when two NMR active nuclei like two protons are close to each other. Because of the low natural abundance of C13 nuclei, the chances of two C13 nuclei being bonded to each other is very small. And so no carbon-carbon splitting is observed. A C13 NMR signal can also be split by nearby protons. This H1 C13 splitting is usually eliminated from the spectrum by using an instrumental technique that decouples the proton-carbon interaction so that every peak in a C13 NMR spectrum appears as a singlet. So there is, the proton C13 splitting is there, but they are eliminated so as to get the singlet NMR, C13 NMR signals. The two features of the C13 NMR spectrum that provides the most structured information are the number of the signals observed and the chemical shift values. But in the case of the H1 NMR signals, we are getting the number of we are having the information, the structure information regarding the number of the signals, the intensity of the signals, the chemical shift values, and the multiplicity. But in this case, we are not having the multiplicity, so we are not getting the splitting information, but we are only getting the number of the signals and the chemical shift values of the signals in the spectrum. So this is the number of the signals. The number of the signals in C13 spectrum gives the number of the different types of carbon atoms in a molecule, and C13 signals are not split. The number of the signals equal the number of lines in the C13 spectrum. So the number of the signals are the number of the carbon atoms in the molecule. In contrast to the H1 NMR situation, peak intensity is not proportional to the number of absorbing carbon. So C13 NMR signals are not integrated. C13 NMR signals are not integrated. So just as we told that we are getting number of the signals information regarding the number of the signals, and information regarding the chemical shift value of the carbon signal. No intensity, no multiplicity, as like that of in the case of the H1 NMRs. So again, the chemical shift value, different chemical shift values are there. And for example, in the sp3 hybridized carbon, the chemical shift value ranges from 5 to 45. But in this case, the proton, if you recall or remind, if you if you have something, the value as we discussed in the case of, this is from 0 to 0.9 to I think so 2 ppm. But in this case, the carbon chemical shift, the signals of the carbon chemical shift is 5 to 45, and so on. For example, in this case, in case of this carbonyl carbon, it is the chemical shift value ranges from 160 to 210. So normally, the chemical shift value in the proton NMR ranges from 1 to 10, or from 0 to 10. You can say, because 0 is the TMS, and then afterwards, then rest of the organic molecules. And in the case of the C13 NMR, the chemical shift ranges from 0 to 220 ppm. So this is the range of the chemical shift values in case of the proton NMR and carbon 13 NMR. It's again the table of different chemical shift values. These are different groups having signals at different chemical shift value in case of the C13 NMR signal. So number of the signals, as we discussed before, different carbon will give you different signals. And this is like, for example, a typical protocol as we discussed before also, but I'm again just to have one side again. So first you are when you are having a molecule, a pure molecule, because purification is done through chromatographic or electrophoretic procedures, and as a result you are getting a pure molecule or pure compound. And when you are getting this pure compound, you perform the IR, the mass, the UV, because before there is wet chemistry, and then instrumental chemistry is there, instrumentation is there. So instrumentation normally we starts with the UV, with the IR, with the MS, and then going on to the NMR analysis. So within the NMR analysis, we first perform the proton NMR, then the COSY experiment is performed, then the C13 NMR is done, then the depth experiment is done, then the HSQC, and then the HMBC, and information deduced from all these experiments will give you the ability or the potential to draw the structure or to determine the structure of the molecule under study. So just having, I'm not going in detail, but just to give you, for example, we are having this compound. At time we are having the structure, but just ignore the structure, and you will perform these experiments one by one. So you will get the H1 NMR spectrum, then COSY experiment will give you some information, then the C13 NMR spectrum, then the depth analysis will be performed, then HSQC analysis will be performed, and then the HMBC, because this is the distortion enhancement polarization transfer, and HSQC is the heteronuclear single quantum coherence. HMBC is the heteronuclear multiple bond correlation, and COSY is the homonuclear correlation. So H1, in this case H1 C13, HSQC, HMBC, and in the COSY case H1, proton. So this is homonuclear, and that is the heteronuclear, and the rest is the proton NMR and carbon 13 NMR, and depth is within the carbon 13 NMR. So this is the molecule we are having. So first we perform the H1 NMR, and the H1 NMR, a proton NMR spectrum will looks like this in front of you. So you are getting these information, which, because for example from this we have to determine, as we discussed before, we have to deduce the information: number of the signals, intensity of the signals, multiplicity of the signals, and the chemical shift value, the position of the signals. So these information we have to deduce, and then we have to tabulate all these information. This is the chemical shift value, multiplicity, this is the spin-spin splitting, this is the coupling constant, how they are splitting with one another, how they are coupling with one another. And this is the integration, the intensity of the signals. And then you will perform the COSY relation, the scalar coupling, the homonuclear coupling, or to determine the vicinity, the environmental, the structure of the proton under study. So when you plot, for example, this is H1 NMR plot, and this is again the same H1 NMR plot. When you plot all these on one on x-axis and the other one on the y-axis, then you will determine, for example, this can be done by the software, but even for example you can do it by yourself as well if you are not having the software. But normally in the NMR nowadays in the NMR spectrometer there are softwares are there. So softwares are there, a number of softwares are there. You can correlate with these things. If there is diagonal, I mean to say, for example, if you can draw this relationship, I mean to say, so you can say that yes, the COSY relation is there, the relation is there. So H1, the COSY shows the correlation between hydrogens which are coupled to each other in proton NMR spectrum. The proton NMR spectrum is plotted on both two-dimensional axes. So the cross peaks not on the diagonal that are symmetrical to the diagonal show the COSY correlation. And then, for example, this is you can see. This is the correlations you can see. The two types of COSY splitting: 3-bond short range coupling between protons 7 and 8. So this is 3-bond correlation, and 4-bond long range coupling between proton 3 and 4, blue correlation. And these are the information you are getting from the COSY experiment, that which proton correlate to which proton. And then the C13 NMR. So C13 NMR is easy to interpret rather than that of the proton NMR, because there is no multiplicity. Just we have to determine the number of the signals and the position of the signals. No intensity, no multiplicity. And then the depth experiment is performed. Depth experiment is performed to determine the number of the CH, CH2, and CH3 carbons. So this can be performed using different depth experiment: depth 45, depth 90 and depth 135. Experiment is performed. And then you perform the HSQC, that is the heteronuclear single quantum coherence. That is the single bond. That is uh, the proton and carbon directly attached with one another. So HSQC shows a correlation between proton. For example, this is the shows which hydrogen are directly attached to which carbon atom. So single bond is there, direct relation. The H1 spectrum is shown on the horizontal x-axis. This one, and the C13 spectrum is shown on the y-axis, that a vertical axis. The HSQC spectrum is most valuable when proton have already been assigned. So you can see these correlations, the direct correlation. For example, you can see the carbon, this the three hydrogen is attached to third carbon. The hydrogen which is assigned number 3 is attached to third carbon. So just we have to go to the structure of the molecule. And this is the information we are getting from the HMBC. That is, HMBC is the heteronuclear multiple bond correlation spectroscopy. That this shows the correlation between proton and carbons that are separated by multiple bonds, not by single bond. HSQC will give you the information, the correlation between carbon and hydrogen directly attached, and the HMBC will give the information with not by direct attachment, but they are correlated or they are separated by multiple bonds. So this is this is the information, or the two-dimensional information we are getting from the HMBC. So with this, I will end my presentation. Hope that it will be a fundamental, not to say not a full explanation of the nuclear magnetic resonance spectroscopy, but I hope that it will be just fundamental, and you will have something in your mind, and this will stimulate, or this will enforce you to study more and to interpret the structure, the spectrum, to deduce the structure of the compound. So hope you will get, you would have got some points or some information. So thanks to all of you for hearing me for about 1.5 hours. Thanks to all of you. And thanks to the IM research group as well for giving me the opportunity to present such things. Thanks to all of you.
Thank you very much, Dr. Nasimullah Qureshi, for your esteemed presence and delivering a brilliant lecture. I am very grateful to you for paving our concepts regarding NMR and explicitly briefing all the aspects regarding NMR. I
Thank you.
thank you. So we are done with the first day of our workshop on characterization techniques. I hope you guys have learned a lot from our esteemed speakers. For tomorrow, I request all of you to join the meeting earlier, I mean before 10 a.m. to avoid the login issues, because we want to facilitate all the registered participants. Professor Dr. Ashraf Ali from China and Professor Dr. Adnan from Swat University will be delivering their lectures on thermal analysis, FTIR, and UV visible spectroscopy. I appreciate all the participants for their interest in research and learning fundamental concepts. Looking forward to see you tomorrow at 10 a.m. Take care and Allah Hafiz.
Allah Hafiz. Allah Hafiz.